Hello and welcome everyone. Thank you for joining us today. My name is Patrick Moran and I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker. Michelle Tanco is a customer solutions engineer and data scientist for H2O.ai. And prior to H2O, she worked as a senior data science consultant for Teradata, focused on leading analytics projects to solve cross-industry business problems. Now, before I hand it over to Michelle, I'd like to go over a few housekeeping items. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded, and a copy of the webinar recording and slides will be available after the presentation is over. Now, without further ado, I'd like to hand it over to Michelle.
Hi, everyone. My name is Michelle Tanco. Like Patrick said, I'm a customer data scientist and solutions engineer here at H2O.ai. And in June, the Driverless AI team and H2O.ai released a new version of Driverless AI 1.70, which allows for adding your domain knowledge into our automated machine learning platform. So today, I'm really excited to talk to you a little bit about how that works, and then we'll dig into the code of how you can start writing your own recipes to enhance Driverless AI. As you may know, Driverless AI is an end-to-end automated machine learning platform. We start with supervised learning use cases and problems. So we're looking at solving things like which class is this piece of data, whether that's a binary classification, yes or no, or multi-classification. We can do regression, so how much will this be? And we can also do NLP and time series use cases. So if you have labeled NLP problems, we can take that raw text and figure out which label applies to them, groups or sentiment. And then for time series, we can do forecasting. So for each of these departments, what will sales be? Or when will this particular part fail? Driverless AI also has automatic visualizations. So without writing any code, you can quickly understand the values in every column and combinations of your columns, look at different correlations, understand outliers, and really make sure that the data is clean and what you think it is. We can handle missing values and outliers, but the cleaner your data is, the better model you'll get. We don't just want to build a black box, though. We really want to understand how models work so we can trust it in our business to make decisions. So we also focus a lot on machine learning interpretability and understanding how the models work both globally and locally. Part of this automated process is also doing automated feature engineering, and that's something we're going to talk a lot about today. Automated feature engineering is taking your raw data and then transforming it to make it either more clean or more valuable for predictions. All of this is very flexible to deploy. So the goal of building in data science pipelines is not just to have a science experiment, but to really put them into production and to positively impact your business. So we make this very flexible and easy with automatically generated production pipeline code, both in Python and Java. So in Java, this is a mojo that you can call from many different places, easily put into your REST server or Java API. And this handles all of the regular type things that happen in productionization that can take a lot of time. So what does your model do if there's a new categorical variable? Or what happens if there's a null value? And that's already handled and easy to deploy. All of this can run on GPUs, so we can go even faster. GPUs are not required, but they can really improve the time to value. And then the feature we're going to really focus on today is bring your own recipes. So how do you add in your own models, your own feature engineering, or your own scores to really combine the domain expertise of your subject matter experts with the broadness of Driverless AI? So Driverless AI is a platform that's applicable across industries and is very general purpose. We haven't focused on a specific use case or industry. So although we're really good in financial services and understanding how customers behave, who's going to churn, we can also be used across any industry, healthcare, telecom, anywhere where we have supervised use cases where we're trying to understand from historical data what's going to happen next. Domain scientists and subject matter experts, though, are the kings when it comes to really understanding their data. So what we want to do with recipes is add in the subject matter expertise into our broad and extensible platform, so you get the generality of driverless AI along with the details of your subject matter experts. This allows you to save time, and it doesn't replace data scientists or people, but rather augments them to make them more efficient and more effective. So if you're not familiar with driverless AI, we're going to talk really quick about how it works in the common workflow. So we start with tabular data. This is data in the form of X, which is predictors, and Y, the predictee. So this is your classification, your regression, whatever value you're trying to predict. We have over 10 connectors to bring in your data from any major data store, so Amazon S3, relational data warehouses, Azure Blob Store, and so forth. Once we bring in our data, we can do automatic visualization, which looks at correlated scatter plots or outliers and really allows you to understand your data and what's going on in the data set. The meat of driverless AI is our automatic model optimization. So this is a genetic algorithm which learns over time what's working and what's not to make the best model for your data. This is made up of feature engineering, where you take your original columns and we create new columns out of them. So some of these are going to be really straightforward, like extracting the year out of a date, because maybe the year is really predictive. Some of them are going to be more complicated, like truncated SVD, which is an unsupervised clustering algorithm that looks at relationships between your data. We can, again, here do just binary classification or regression, but we can also do time series forecasting, and we have transformers for text, so we can do NLP as well. In addition to building new features, we're also simultaneously trying different algorithms. So by default, this is things like XGBoost, maybe TensorFlow, LightGBM. But then what we're going to talk about today is how you can also bring in any machine learning model that you want to test in driverless AI. So we have many examples written for you, but you can also write your own, and that's what we'll be doing today. Finally, we then tune these models, so looking at which hyperparameters are best. And all of this is happening in parallel, and we're learning over time to build the best model. Finally, once you have a model, there's a couple things we'll want to do. We have automated model documentation, which explains everything that happens in experiments and how a model works. So you have model governance and understanding how that model really makes decisions. We also have machine learning interpretability, which uses some of the industry best practices for understanding how a model makes decisions. So these are things like Shapley values, K-line, partial dependency plots, which allow you to look at a row of data and see why driverless AI is making the prediction that it is. And this also helps when we go into productionization to understand how to change bad behavior of customers. Maybe if you see someone's going to churn and you know exactly why, you can go in and save that. Once you have a good model that you understand, we then have our automated scoring pipeline to quickly put that into production. So then what we're going to be focused on today is our bring your own recipes. So this is a way to augment that middle step, the automated model optimization, with your own data transformations. So this could be domain knowledge, like specific dates that were end of quarter or major sales or marketing events. These can be algorithms. So if there's a specific type of algorithm that a domain scientist wants to try on their data, and this can also be scores. So maybe you don't want to optimize for F1 score, but actually false discovery rate is more important for your business. And this really allows you to bring in anything that you need for your business into driverless AI and into that genetic algorithm. So your audit items will compete with ours, and we'll see what the best model is. So we're talking a lot about recipes. Today we're going to first get into the meat of what a recipe is, how it works, and what the value of it is. We're then going to write a transformer, a score, and a model algorithm, and talk about what's required for each of those. We'll go through a couple advanced options, and then at the end we'll talk about how you can get help from us in writing your recipes. So a recipe is a piece of that end-to-end machine learning pipeline. So this could be at the beginning in the data prep, taking your raw data and pulling out and making new, more interesting pieces of data that help with prediction. And this is known as either feature engineering or a transformation. A transformation might also be bringing in additional data sets. So maybe you have a zip code and you want to know what the population of that city is, or you have a specific date and you want to know what the weather is. So we might bring in new data as well. We also are going to model the data, and different data sets and problems will benefit from different types of algorithms. So XGBoost might be better than LightGBM, might be better than TensorFlow, depending on what you're trying to solve. And then the way that we pick the best model is a score or a business metric. So this could be a sort of generic score like log loss or F1, or maybe you know the cost of a false negative and the cost of a false positive, and you can actually optimize for the cost of a model in your business. So these are each pieces of this machine learning pipeline. And BYOR stands for bring your own recipe. So we have over 40 transformers, 8 models, and 10, I think, scores. But now you can bring in your own. So if there's a transformation that makes sense for your business that we don't have, you can add it in. By providing your own custom recipes, you can get a little more control over the optimization and also add in information from your domain experts. So we'll look at today open source recipes. The team has built over 90 so far, and you can add your recipes to our open source repository, or you can keep them internal for yourself. Now, why do you want new recipes? Although driverless AI is extensible and really predictive on its own, that domain expertise can really improve our models. So recipes are flexible, extensible, and customizable, and we add them directly into driverless AI. So you don't have to write your own recipes. You can use recipes other folks have had and put them right in driverless AI and test them out. Our open source repository of recipes, we have over 90 right now, is created by our Kaggle Grandmaster team. We have over 12 Kaggle Grandmasters at H2O AI, and they're helping make sure we have the best recipes to really improve your model. Recipes are easy to upload, it takes one click, and then driverless AI actually tests them when you upload it. So if you write code and you're not super sure if it's going to work on data, or maybe you haven't thought of every use case, like how does this model handle nulls, we'll test all of that at upload and return back error messages if you don't pass the acceptance tests. So this is a way to start debugging code and using driverless AI to maybe get a little better at writing Python code as well. And this way, every business can have their own recipe cookbook. You can add them into ours again, or you can keep them private for your business. And then I just wanted to give one example of using a custom recipe before we start digging into how to actually build them. Here we have a text data set that's tweets about airlines. So folks are saying how they felt about a flight, and the sentiment has been calculated ahead of time as either positive, negative, or neutral. And we're trying to predict this using driverless AI. So on the left, we have a default driverless AI experiment. It's taking the text and it's building text features using TF-IDF, and this is all completely default settings. And we can see we get a log loss of 0.6. So log loss is a metric where we're trying to get as close to 0 as possible. On the right, we went into the expert settings of driverless AI, and we turned on our TensorFlow CNNs. So this is character-based embeddings and word-based embeddings. And then we ran our experiment, and we got a much better log loss. So we saw just by turning on these advanced features, we improved our model. Now, these are still features that come out of the box with driverless AI. What we did in our middle experiment is we uploaded the sentiment recipe, which is an open source recipe that someone has written, and we're actually going to look at it today. And we added in that sentiment, and we can see it on our variable importance list. So it actually improved our model, and depending on how important it is, knowing if someone is giving a positive or negative review of their flight via Twitter, this could be really important. So just by adding in this really easy recipe, we are able to improve our model even more. If you'd like to learn more about how recipes work at a high level, how driverless AI works, and then why you might want recipes, I highly recommend you check out Arno's webinar from last month that's extending H2O with recipes. And for the rest of today's presentation, we're going to focus more on the Python side of things and how to actually write these to take your domain expertise and put it into driverless AI. All right, so to start with, let's talk about the process for writing recipes. To write a recipe, one of the first things we recommend doing is writing this in straight Python and testing it on some sample data. So we don't need to write it up as a driverless AI recipe. It's just writing the code that is going to, for sentiment, say, take a piece of text and get out a sentiment of it. On the right here, this is the development environment that I use, PyCharm. Really all you need to, we'll talk about this in detail a little more, but all you need to write a recipe is somewhere to write Python code. So this could be just a text editor, or it could be somewhere where you can actually run Python like PyCharm or Spider or Jupyter. So the next thing you would want to do maybe is download the Driverless AI recipe repository, and here you have all the different examples. So I'm going to show you this in just a minute. But then the third thing to do would be to look at the recipe templates. So we have a template for transformers, models, and scorers, which shows you everything that you can do in a model and everything that's required in a recipe. So we'll go ahead and check out the GitHub. So on the GitHub, which if you're going to write recipes, I highly recommend you download this. We have an overview of how they work, but then maybe more importantly is we have all of the recipes. So you can download and put these in your development environment for easy access. The way I do this, I have PyCharm, and I have all of the pre-existing models and recipes and transformers on the side, and I can easily go through and say, okay, well, how does CapBoost work? Because I want to build something similar to it. So we'll go back to the PowerPoint and sort of the outline of how you might write a recipe. All right, from the technology side, what it takes to actually write these custom recipes, well, the only thing you actually need is somewhere to write Python files. So if you wanted, you could use a text editor like Atom or whatever else to just write your script and then upload it to Driverless AI, and you don't actually ever have to run them locally. To actually use or test the recipes, you need access to Driverless AI 1.7 and higher. 1.7.1 will be released later this month. Bring Your Own Recipes is not available in the current LTS release series, so 1.6.3, or any of the versions of Driverless AI before that. So you do need 1.7 or later. So that would be to test code in Driverless AI. Remember, we have all those acceptance tests. If you want to test locally, what you're going to need is Python 3.6, and then you'll probably want to install NumPy, data table, and the Driverless AI Python client. So we can use pandas for all of our model and transformation and scoring needs, but the data is going to come in as a data table object. And then the Driverless AI Python client, you can actually download from Driverless AI if it's running. So let's show that. So in Driverless AI, we can click on resources, and then we have the Python client. And this will download the wheel file, which you can then install. All right, and then to write recipes, really the only skill set we need is some comfort with Python. So if you've written code before, even in a different language, you should be able to pick this up fairly easily, and we'll talk through the individual needs of it, but familiarity with Python is a good skill to have for this. All right, next we're going to talk about how to test recipes. So on the right here, we have an example of how you upload recipes. So we'll talk about that more in a little bit, but you can see as soon as we upload a recipe, acceptance tests are run. So this will be one way to understand how your model is working. And our acceptance tests include things like missing values. It gives example data for binary and for regression to understand if your model or your transformer can handle all different types. And it will return back pretty easy to understand error messages if there's any sort of issues, so you can go through and fix that. You might also, if you have a recipe you're adding a lot of pieces to over time, you might want to use the Driverless AI Python or R client to automate the process. So there's an example in the repository of how to do this for a transformer. But basically, it connects to Driverless AI, it uploads your transformer and returns back any error messages, and then it runs a sample experiment and shows you that the transformer was used. So if you're doing a lot of testing and don't want to click through the UI lots of times, that might be a good way to go. And then we'll see this when we start jumping into the code, but the three recipe types, we're basically extending a base class. So to run it locally, we need to have that base class. And in GitHub, we have the dummy version of the base class. So if you want to test running your code and see if it will build locally, we can use that dummy version to do that. This will make a little more sense when we jump into the code. All right, but then what happens if you get stuck while writing a recipe? Well, there's a couple things you can do. The acceptance test error messages should give you a direction to go in, and that includes stack traces, and you can also look in the logs. The stack traces and experiment logs are always a good place to start, and then also save them for the next steps. So we can look at the FAQ on the GitHub. So this has a lot of frequently asked questions, which maybe the issue you're having is answered there. We also have tutorials. So available starting today in our tutorial is a getting started. So this isn't for writing recipes, but rather for using them. So if you want to understand how to upload the recipes and what the UI should look like when you do, this recipe is a great place to start. And then on Friday, we'll actually have a new tutorial that will be a partner with this webinar, and it will walk through how to write recipes. So that would also be a good place to go if you get stuck. And then finally, the reason for saving these logs in stack traces, you can always join the H2O community on Slack and ask your questions there, and our expert data scientists, Kaggle Grandmasters, will answer, and we can help you start to write these recipes. And that's where having the logs would be good, because that's the first thing that they'll ask you for. All right, now let's jump into how we're going to actually start building these. If you're familiar with scikit-learn, you'll notice that the API for writing recipes we're about to look at is going to look really, really familiar. And this is based off of how scikit-learn it works. So the first is our feature engineering, or those transformers. So every transformer is going to have two main parts: a fit transformer, which takes the X and Y data and changes those X variables. So this might pull out the year from a date. It might do some sort of arithmetic between multiple columns. It might do some sort of target encoding. And we can also add in new data here. So maybe it looks at the zip code and uses a zip code package to pull populations or cities or whatever else. And then the transform data, the transform is what's going to get called when you actually run the model and get predictions. So that transform will be inside the scoring pipeline. So when you actually productionize this, you can get this transformation. It will also be used on the validation and test data sets. So it doesn't have access to Y, and it's just fitting the data, or it's altering the data based on what happened in the fit transformation. The next is our models, or the next is our scores. So scores could be lost or gain functions, or they could be something like F1 score. So we have F1, F2, and F05 by default, and these are basically different ways of looking at the precision and recall of a model. So precision would be how good or how right is my model when it says that an event happened, and recall would be how many of those events did I have. So F1 score is a perfect harmonic mean of the two, whereas F2 gives recall a little bit more weight. But maybe for your business, you want to give recall a lot more weight, so you could write an F4 or an F6 function. We can also do costs and rewards. So maybe you're trying to get as close to zero as possible. It's a type of loss function. Or maybe you have a profit function where you know how much money you'll make if you predict something right, and so you can optimize for getting as high as possible. And then finally, we have our machine learning algorithms, and these have two main functions. The first is fit, which actually fits the model. So this gives us access to basically every machine learning ecosystem. We've pre-written all of the open source H2O functions, so you can see those in the GitHub, but you also have access to write all scikit-learn's models. We can do PyTorch, Keras, we can do Intel's V8, DAL, basically any model that you've been using outside of Driverless AI, we can now write and put in Driverless AI. So the fit function will fit that model, and often this might just be calling some outside machine learning model, and then the predict actually makes predictions. All right, so now that we've sort of overviewed on Now that we've sort of overviewed on the process of writing models or writing recipes and how they work, let's jump into the code and start building a transformer. So the transformer we're going to build today is a summation of multiple columns. So by default, Driverless AI comes with mathematical interactions, and it will already take two columns and add them, subtract them, multiply, and divide them. But we might want to add up more than two columns. So what we're going to write today is a function that will take three or more numeric functions and three or more numeric columns, and it will just add them up and give us the sum. So in this case, we're taking x1, 2, and 3, and we're adding it up to get these numbers. So 10, 5, and 3 is 18, and this would be our new column, which might be predictive in our model. There are three main steps to write a transformer. The first is extending the base class. So there are two base classes for custom transformations. The one we'll be doing today is the generic one, which is going to be most of your transformers, and this is the custom transformer function. You can also do a custom time series transformer if you want to have a time series specific transformation. And a good example of this would be like Facebook's Profit or Arima. So both of these are available on the GitHub to see how they work. But we're going to focus on the generic transformer today. The three packages we're going to be using is NumPy, data table, and then this custom transformer class. So this is actually part of Driverless AI and what we're going to be referencing. So once we've extended our model, the next thing we're going to do is tell Driverless AI which columns are allowed to use this transformer. And this is done in the getDefaultProperties method. So it returns the dictionary of 4 types. The first is the column type that's allowed. So these are our options for column types that are allowed, and we do need to choose a single value. Most of these are going to be pretty straightforward. So all would return every column type, whereas any would return a list of some of the column types, but any of them would be allowed. And then we have a kind of a special one. Numcat would be if you wanted both numeric and categorical functions. One thing to keep in mind here, because we have single column types, if you want to write, say, a transformer that works on all string values, we're going to end up writing two. One that does text, which is really long strings, and then one that does categorical, which might be our smaller strings like cat, dog, mouse. But usually those are going to be two separate categories. So then after saying what type of columns are allowed, we then give a min and max. So for our sum transformer, our minimum number of columns is going to be 3. We don't need to do 2 because that's already handled by a different transformer that comes with Driverless AI, the interactions. So we're going to say we want at least 3 columns, but we'll take all of the numeric columns. And every time this gets called, Driverless AI will choose a number between 3 and all numeric columns. And then for the most part, we're going to keep this relative importance as 1, but we can make this number higher if you wanted your custom transformer to be more likely to be used than the default transformers. So it's just a way to give it a little more importance in that genetic algorithm. So once we've told the Driverless AI what data is allowed in this transformer, we're then going to actually fit the transformer. So in your fit transformation, in this case, what's going to do, it's going to bring you a data frame or a data table data frame of the X values, so the predictors, and it's going to give you the Y values, which you might be doing if you're like target encoding or so forth. And so this will be in the form of a data table, and you can return back a data table, a pandas data frame, or a NumPy array. Driverless AI can automatically handle any of those. So what you might see in several of the transformations as you go look at them in GitHub is the first step here might be taking that data table and turning it into a pandas data frame and then doing something pandas on it. So for the most part, we recommend doing data table as it's super duper fast, but there might be some things if you're more comfortable with pandas, you can absolutely change it and just return it there. So in this case, this is our data table syntax for taking every column. So we're saying for the range of the columns I've brought in, I want you to get me the value of that column, and I'm going to add them up. So I'm returning basically a single column that has summed up all of the numbers that I was given. And so this will be for every row. So this is our fit transformation. And the next thing we're going to do is our transformation that will get called on the test data. So again, this can be returned as a data table, as a data frame, or a NumPy array. In a lot of use cases, your fit transform and transform function are going to do the exact same thing. They're not going to use the Y. So if you're doing time series or if you're doing something where you need the Y, the code for these two functions might be different. But in this case, I am summing the same whether I'm training or testing. So I actually rewrote my fit transformation just to call my transformation so that if I ever wanted to change this, I wouldn't have to remember to change it twice. So just sort of a good best practice to keep in mind. But in this case, our transformation on new predictive data is going to be exactly the same as how we fit. And so we just have this same line of code that is taking every value in the row and adding it up and returning that added up. So then the last thing we have to do is say when this transformer should be used. So we looked at what columns are allowed and we looked at how it actually works, but there might be times when it's appropriate or not appropriate to actually use this column or this transformation. So we start by saying what are the types of machine learning problems that are allowed. So in this case, this can totally work on regression, binary, and multi-class. It's always allowed. But these three options are going to be more important, say, when you do models or scores. Maybe there's only certain types of machine learning problems that they make sense for. We need to say if this transformer returns a number or not, because there are some models which cannot take strings as input, for example, GLM. So if this were to return back a string, we wouldn't be able to use that transformer directly into GLM. So we have to tell it that. We want to say if the function is going to be reproducible or not. So Driverless AI has the ability to create reproducible models so that if you run it on the same hardware, you get the exact same features, exact same score. So if this transformer isn't deterministic, then we need to tell Driverless AI so that we know not to use it if our end user requires reproducibility. And then finally, we might say if there were any types of models that should or should not be used for this. So maybe our transformer isn't going to work in TensorFlow or something like that. Or maybe we only want it for TensorFlow. So in that case, we would have a list of strings of the models that we would or would not want. So let's look at one more example of a transformer. In this case, we're going to be doing the sentiment function that we looked at earlier with our airline data set. So the sentiment function actually is using a different package called TextBlob. So we're going to see a little bit new line of code here, and this is the model needed by name, TextBlob. So the first thing that's going to happen when Driverless AI sees this is it's going to actually download and install TextBlob. So if we had a specific version of this that was required, we would just say what that version was, and then it will make sure that package is available for us. In terms of what columns can be called on sentiment, we're looking for text columns because we don't want, sentiment of a number that doesn't mean anything. And we only need one column. So in this case, we're not doing comparison between columns or anything. We just need one column that we're going to call sentiment on. And then this can get called for each of our text columns if there are several, but we only need one of them at a time. In this case, we actually defined a new method that does our sentiment analysis. And so we could have ran this in our transformer or fit transformer, but just to be clean, we have a little function that uses TextBlob. So it imports TextBlob, it uses TextBlob to get the sentiment, and then it returns that sentiment. Our fit transformation is going to be identical to our transformation. So again, we're going to just call that final model. And then here, we're actually going to use that function. So we're taking each row in our data set, we're going to make it a pandas data frame because that's what our function is looking for. So we're making a pandas data frame, and then we're actually going to use a lambda function to call that sentiment analysis. So then what's going to get returned here is a column that is the sentiment. So this is what this function will do for us. All right, so that's a quick overview of writing transformers. I'm going to take a quick minute to look at questions really quick. Okay, question on if you need to write a recipe or not. If the original feature is already in Driverless AI. So I would look in the documentation for this. We have all 40 transformers listed there. There is not currently a feature where if you upload a transformer, Driverless AI will say, hey, I already have this. So we'll just want to check the documentation and see if what you're interested in is already there. Right, okay, so there's another question that's asking if there is something in Driverless AI that tells us that we might want to add in a custom recipe or we might want to do our own feature engineering. In that case, no, not really. So Driverless AI is really extensible and usable on lots of different use cases. But in terms of when to add in recipes, well, that's really when you need to talk to your subject matter expertise or domain experts to understand if there's specific business knowledge that you're missing in sort of the broad platform. So that's sort of the answer there. So it looks like we don't have any specific questions on writing a transformer. I'm going to jump back and we'll now get together and write our score. So scores are what we optimize the model for, and it's how we say if a model is good or not. So the score we're going to start with today is false discovery rate. So basically this is for binary classification, and it looks at what percentage of what we're classifying true is actually false. So you can, this is basically a type 1 error or the opposite of precision. So the algorithm for this is going to be count of our false positives divided by the sum of true positives and false positives. So it's the things we got wrong divided by everything we said was the same. So it's a pretty straightforward algorithm. So the steps of building our score, well, the first step is basically the same as a transformer, and all we have to do is extend the base class. There's only a single base class for scores, and it is custom score. So we'll say, okay, false discovery rate scores, and I'm going to extend the base class of custom score. And in this case, you'll notice I have a couple more imports I brought in. I'm specifically going to use scikit-learn's label encoder for taking my label data, which might not be 0, 1, it might be yes, no, or cat, dog, or any two labels, because this is for binary classification. So we're going to use scikit-learn's label encoder for that. And then we're also going to use scikit-learn's confusion matrix. So we could ourselves count true positives and false negatives and so forth, but then that's extra code we need to test and make sure it's correct. So we know scikit-learn used pretty regularly and has been tested well. So we're just going to just use that function. All right, the next thing and main thing we do for a score is actually write the score. So the scoring function has 4 inputs. First is an array of actual values for our target column. So this is whatever the value actually is, and it is going to be text if your raw data is text. The predicted value is going to be a numeric value. So for regression problems, this is, in your feature space, this is a number that's appropriate for your regression. For binary classification, it's going to be a single column that is a number between 0 and 1. So how likely we are to be that one class. And then for multi-classification problems, this is actually going to be a probability for every class. So there will be multiple values. The sample weight is optional, but Driverless AI has a way when you run experiments to say, some rows are more important than others. And so the sample weight would bring in and give you your key on which rows are more important. So that's going to be whatever column the user of Driverless AI said was a sample weight column. And then labels are for our classification problem, so they just tell us how to label the data. What this function is going to do is return some sort of flip score. So it will be a number that we're either trying to optimize to be high or low, and we're going to tell it that next. So our actual code for this, the first thing we're going to do is use that label encoder to label our data so that it's a value instead of being between 0 and 1. Well, for false discovery rate, we need to know if it's a 0 or a 1. So we're going to label our actuals into 0s and 1s, and we're going to take our predicted and label it as a 0 or 1. So in this case, we're going to be using a default threshold that we have decided. So, you might use 0.5 by default, or maybe for your business case, you want that to be higher or lower, but we'll pick a threshold. So we're basically making our actuals and predicted values both be either 0 or 1. We're then going to call sklearn's confusion matrix. So we're calling the confusion matrix, and we're getting back the true negative, false positive, false negative, and true positives from our confusion matrix, and then we're returning back our algorithm that we talked about. So the false positives over the total positives we predicted. Now, this is one of the places where we're writing code that we might want to, really pay attention to our acceptance tests or thinking this through. If we had no positives in this data set, we're going to divide by 0. And so we might want to add in a little check here that says, if we're dividing by 0, either error out safely, or, you maybe give a default value of 0. So just something to keep in mind as we're writing these, what checks you might need to do. All right, the last thing we have to do in the score is tell Driverless AI what a good score is and when to use a score. And so in this case, we say, well, we're only using for binary classification. We don't want this to be used in regression or multiclass because that doesn't make sense. And then we need to say, well, is it better to get bigger or smaller? So in this case, we have maximize as false because we're trying to get as close to 0 as possible. The perfect model would be if there was no false positives. And so the perfect score, the reason for the perfect score is it tells Driverless AI that it can stop working. So if Driverless AI was going to build 200 models and on the 100th model it got the perfect score, there is no reason to keep working, right? We've optimized, we're done. Let's save the CPUs. And so then if we hit that perfect score, we'll go ahead and stop. All right, let's look at a second function. In this case, we're going to do a regression function, and we're going to be looking for the largest error. So this is going to be super sensitive to outliers and would be a way to find out, maybe you don't care about the overall score in the model. You just want to know what's the worst I ever was in my predictions. So in this case, we don't have anything special we need to import. We're going to name this function my largest error score, and then we can give it a description and display name. So these are going to be nice descriptions for Driverless AI. So it will be called largest error rather than my largest error. We call largest error, and then if we hovered over this, we would see this little description, which is my largest error score for regression. So we can add in descriptions and display names for transformers and models as well. And if we don't, there are default values that will be set. The largest error only works on regression problems. So we say no to binary and multiclass. And then we do not want to have a largest error. So we're going to false on a maximize. And again, our perfect score is going to be 0. So this one's pretty straightforward. What we're going to do is find out the absolute value for every actual in prediction. So now we have an array that is basically the residuals of every prediction. This function, if there are sample weights, so if you have any columns that have been flagged as more important, it will return back the max error for just the sample weighted columns. And if not, it will just return the generic max error. So if you have a sample weight, say you have 2 sample weights, so you have a sample weight of 1, sample weight of 2, and 3, maybe you would want to rewrite this a little bit differently and say you don't just want the max for any sample weight column, you want the max for the most important. And this is where you can start to get into the specifics for your business case, because what sample weight means is going to be different for every business problem. All right, that's our quick overview of scores. So we're now going to jump into how to build a model algorithm. So models are a little bit more complicated than our transformers and scores. So we're going to do a high level on models today. And then we'll talk about, how you can learn more and how you can really get going with them. So our model algorithm we're going to look at today is sklearn's extra trees. So there's an extra trees for classification, and there's an extra trees for regression. And so this is just another algorithm that might give a little bit of a different prediction than, say, random forest or XGBoost, and it might be something that you're interested in trying. All right, just like transformers and scores, the first thing we're going to do is extend the base class. Now, there's a couple more options here for models because we have 4 different types of models. So what we'll look at today is just a generic model, but you might also have a custom time series model. So this is going to have everything that we talk about today, but it's also going to have an update function because time series models need to know how to look at past data, especially when you're doing your scoring and you have any new values you want to use. We also will have a TensorFlow model. So it's going to be a little bit different models that use TensorFlow. And if you want to get really fancy, you can have a time series TensorFlow model. So each of these are base classes. They're going to be a little bit different and add on a little bit more options. Our extra trees model, well, we need to import that function from scikit-learn because we're going to be calling it. And then we're also going to be using that label encoder again. All right, the first thing that we have to do is fit the model. So we will bring in our X and Y values, and if there's a sample weight column, we'll bring that in too, so which rows are maybe more important than others. And then if you have a validation data set, a specific validation data set you want to use, we can bring that as well. So there might be sample values for our validation data set. What we're going to do first in this function is we're going to save off the names of all of the predictors that came in, and we'll see why we do that in just a moment. Next, well, we want this function to work for both classification and regression, so we want extra trees for every ML problem, so we're going to handle that here. So we're going to say if we are binary or multi-class, so if there's more than 2 or more classes, we're going to use the label encoder, and then we're going to call the extra trees classifier. If this isn't the case, that means it's regression, so we're going to call the extra trees regressor. So now we've created this model object, which is scikit-learn's extra trees, the appropriate version for whatever model we're running right now. And we are going to put this into NumPy format and then fit it. Our raw data is in NumPy format and then fit it. Now, one thing we want to keep in mind, if you're implementing a model that can't handle misleading values, you need to account for that in your model code. So if extra trees can't handle missing values, you need to have something here that either puts out an error message, or maybe you drop those rows, which is definitely not recommended, or maybe you impute the value with the median or mode. And so we need to keep that in mind when writing model functions. Just sort of a warning note there. One of the acceptance tests when you go into Driverless AI is data with missing values. So that's something you might see if we don't think about this, is Driverless AI won't actually let you upload the recipe because you can't handle nulls. So then after we've done any specific prep for our algorithm, which would be this missing value work, we will fit the model. And after we fit the model, we're going to set some model properties. And so the model properties are 4 options that Driverless AI needs to know. One, it needs the model object so that it can do predictions with it later. Second, it needs to know what features were used to create this model. And so that's why we saved off our original columns earlier. So we want to know the names of all the input features that went into this model. We also want a list of importances. So if you've seen Driverless AI, the most important features are shown at the bottom as each model is being built. And so we need to populate this list. So lucky for us, extra trees comes with a function feature importances, which does that for us. So in this case, all we're doing is just returning back that value. But if your model doesn't do that, something you need to keep in mind. And then also any iterations that we did. So this is just how many times we have built our model. In this case, it's using a parameter, and we will talk about parameters soon. So this is our fit function. Again, to review, we handle any model types we want to, so regression and classification. We handle if there's any null values, and then we fit our model and return back the features that we need to about it. The last thing that we're going to do with the model is we need our predict function. So in this case, we will get our model properties. So this is these 4 features from previously. So the only thing we need in predict is the actual model. And then if our predictions can't handle nulls, we need to do something about that right here. So if this model is going to break, if there's a null value, then we need to put in some sort of checking for that here. And then we will do, we'll handle both regression and classification. So if it's a regression, we're going to just call the predict function because we know this is a extra trees regression model. And if there's more than one class, that means it's binary or multi-class, we're going to do predict probability. And this is the function for the extra trees classifier model. And so that is what we need to build a model. We have to say what packages we need, we have to fit the model, and we have to predict. We're going to jump over really quick for a model into the model template. So this is in the GitHub. So if you download the GitHub or you're looking in GitHub, you can go to models and you can choose a model template. And so we can see everything we need here in a little more detail. Just like we saw for score and transformer, we can say, you know, what kind of use cases should this be used for? And there's a couple other features we might want to add in. So these are all documented and detailed really well here. And you can get a little more information about like how to, this is what I'm looking for, how to write that fit model and what each of these features are. So something I definitely go check out. All right, really quick, let's talk about a couple extra things you can do with models. So we did a couple basic examples today. One of the things you might want to do is import a package. So we talked about this for sentiment, but here's another example where maybe we would want to do it globally instead of inside of a class. So here's how you say the specific version that you want. So we can say, okay, I want to install this specific package and I need it for this full transformer. We can also extend our custom recipes. So if we have several recipes that are really, really similar, we can write it once as a base class and then write other recipes that call from these. So in case of the fuzzy matching, you might want different methods for match ratio. So we actually are going to create one fuzzy-based transformer function, which you can see in the GitHub, and then we're going to create two more functions, and the only thing that's different about these classes is which method they use. So everything else they're going to do by default in this fuzzy-based transformer, and we're just changing the method that they use for fuzzy matching. Same with the zip code. There's a single zip code transformer, which does all of the brunt work of using the zip code package to get information about different zip codes. And then we have different classes, and what each class is going to do is just return different information. So it's just a way to extend your recipes. We can also set default parameters and mutate the parameters. So this is particularly important for models. In our extra trees, we might want to try different estimators or different numbers of trees. And so we can try many different trees depending on, in this case, depending on our accuracy setting. So if we're doing a low accurate or fast model, we might only do a really small number of trees. So just something we can check out, and there's examples in the model documentation, but things that you can do. And then the last thing I wanted to mention, when writing these, you might want to do logging. So we can actually write logs into, write notes into the experiment logs. And this will be a way to understand, you know, what's happening, what values are being used as you're debugging functions. So you'll have this stuck at the end so you can see how to do this. But just a good thing that's with your debugging code, or if you're not sure your model or transformer is working the way you want it to, you can leave notes in the logs to see what's happening. All right, so at this point, I think we're almost out of time, so I want to open up to questions. If you have more questions generically on how this works, please check out the GitHub repo. This includes an FAQ of frequently asked questions. We also have a model architecture that explains, you know, in detail how driverless AI works and how all of these pieces fit into driverless AI. And then you can always join our community channel and ask us questions there. All right, Patrick, I will give it back to you.
Great. Thank you, Michelle. We do have one question I'm seeing here that says, one of the earlier slides said that deploy low latency scoring to production. Where do the models get deployed? What are the deployment options? And what is the scoring latency?
Oh yeah, okay. So for driverless AI, when you finish an experiment, you have production-ready code that's created. So this is not a custom recipes question, just in general for driverless AI. So this can be a Mojo or a Python scoring pipeline. And so if real-time is important to you, then Mojo is probably the way to go. And this is production-ready Java code that can sit inside of a REST API, a Docker container, a Java API. The places it can be deployed are basically limitless. We have one-click deployment to Amazon Lambda. And then latency can be particularly fast. It really depends a little bit on what transformations are happening and what the data size is. So I don't want to say like an exact number of, microseconds or milliseconds or seconds, but it can be very fast. One thing to keep in mind with custom recipes is they are Python snippets, and depending on the recipe, it might be tricky to write the Mojo for them. So if you want to look at how to write Mojo code, the log transformer is a good place to start. So we'll go to transformers, numeric, and log, and our log transformer has Mojo code. But some of the transformers, like if you did a model with TensorFlow or a transformer with TensorFlow, well, TensorFlow is not in Java, so you can't really have a Mojo, at least not yet. We're working on it. So that's my it depends question for how they deploy. It really is how you're deploying models, but we have lots of options.
Great. There's another one here that's asking, are there any plans for supporting recipes in R?
Yeah, so currently you can have recipes in anything that can hook up to Python. So like we have models, well, most of driverless AI in the back end is C++. And then like our open source models are actually written in Java, but we're connecting to them through Python. So direct R, I'm not positive and would need to check on if that's roadmap. But today, if you're able to call it from Python, so if you had like R code that did something and you could connect it to Python, you could have a recipe in R, kind of.
Got it. Okay. I want to thank Michelle for taking the time today and doing a great presentation. And I want to say thank you to everybody who joined us as well. And we hope to see you at our next webinar. So have a great rest of your day and take care.